Barry, one of the core questions that I've asked myself my whole intellectual life is the material world all there is? However deep and however broad the material world comes beyond our current understanding, whatever is physicality, naturalism, materialism, however we want to define the term, is that all there is? And one of the techniques that we try to attack that with, or to stress test it, if you will, is the area of philosophy called metaphysics, which deals with the most fundamental characteristics of the world. And as you analyze that, are there things that pop out or forced out that are not natural in our understanding of the physical world? You've dealt with all of these characteristics. How do you analyze the use of metaphysics in testing the naturalism or the physicalism of the world?
So I do like a sort of physicalist view of the world, though I wouldn't exactly call it a material view, because matter may turn out not to be material exactly.
Right.
But
that's an archaic word. Yeah.
Yes, but here's an interesting example. So there are some features of our world which we want to be explained, and sometimes there can be scientific-like explanations. So, for example, we might explain the location of the Earth in the universe. And at one time, people who thought of themselves as philosophers or metaphysicians argued that human beings are clearly very important, and so the Earth must be in the center of the universe. So they had a kind of metaphysical reasons for locating it. They were, of course, completely wrong about that. And there's a scientific account of where the Earth is located, around us, revolving around a star that's revolving in a galaxy, among billions of galaxies, hundreds of billions of galaxies. Here's another interesting example about that: the nature of time. So time seems to all of us to do something. Everybody uses metaphors like time passes, time flows, time has an arrow. The famous Omar Khayyam wrote something like, "The moving finger writes and having writ moves on, and you will never get anything back from it," or whatever, something along those lines. So the question is this something that's deep in the metaphysical reality of the world, or is there a scientific explanation of why it is that time has temporal processes have a direction? Now, there is definitely a directionality in this sense. Ice cubes melt. They don't form spontaneously out of warm water. People grow older. They don't grow younger. We remember things that happened a long time ago. We don't have the same kind of knowledge about the future. We can affect or influence things in one temporal direction that we call the future, not in the other. The question is this to be explained by metaphysics, by something about the fundamental metaphysical nature of the world, or something by science, or some combination of the two? I'm interested in seeing how far one could go by scientific explanations, and I think one can go quite far without introducing metaphysics into the explanation. I think metaphysics gives pseudo-explanations in this case. So a metaphysical idea that's introduced, which some of my colleagues and some physicists also have, is that time itself flows like a river. Now, I don't really understand that, in part because flowing like a river means being at different places at different times.
Yeah.
How can time do that? Okay? But maybe you could make sense of it. I'm not sure it's contradictory, that form of words, but I don't see it helps very much. Some philosophers think that time, unlike space, has an intrinsic direction built into it, that at every point in space-time, there's sort of an arrow which says, this way to the future. And the laws, in some way, respond to that arrow in how to evolve things. I don't think that's a very good view either. What I do think is that physicists have discovered a general view about the world which accounts for certain physical processes, which can be expanded into an account of the directionality of all temporal processes. The account was thought up by a very important physicist named Ludwig Boltzmann in the late 19th century, and what goes under the name of statistical mechanics. Within physics, sometimes statistical mechanics is taken as a kind of compendium of recipes for how to calculate the values of what will happen, what the temperature of a system will be after a certain amount of time, or how long it will take for an ice cube to melt, or something like that. But if you really think about it, the way Boltzmann thought about it, it's a theory about the world. It's part of a theory of everything. What Boltzmann presupposed was that there was something like a probability distribution over all the possible microstates that the universe might be in, compatible with its macro state. The macro state has to do with the way things appear to us observably, maybe having to do with the temperatures of small regions, the densities, the electromagnetic radiation, and so on. And there are many, many microstates that could realize any such macro description, and there's a probability distribution over all of them. Boltzmann had a particular way of expressing that probability distribution. It's a very simple way, and it followed from that ice cubes, typically ice cubes when put in warm water towards one temporal direction, will melt. And so it looked like he solved the problem. Why is it that ice cubes melted? In fact, this comes under the question of why the second law of entropy exists, why the second law of thermodynamics exists, why the law of entropy of a system increases over time. Because it's highly likely, given this probability distribution, that if its entropy isn't already maximal, it will increase in one temporal direction. Unfortunately for Boltzmann, his probability distribution also had the consequence that its entropy was bigger in the past. That's ridiculous. We don't think that. And this drove Boltzmann crazy. He actually committed suicide near Trieste, the place I've been to a few times, maybe for this reason, maybe not. But the problem was solved later on by Eddington and by Richard Feynman, and also it's been put in a very nice book form by David Albert, who's a philosopher-physicist, and Sean Carroll, who's a physicist. And it's the idea, and by Roger Penrose, and it's the idea that the entropy of the universe was very, very tiny near the start of the universe. So this connected up this question about the directionality of processes with cosmology. Okay, and that's a really interesting thing. Sorry.
The implications of that for physicalism is what?
Okay, I think it's a very important implication, because I think now that this idea of Boltzmann's, as developed by Eddington, Feynman, Albert, Carroll, a little bit by me, and so on, has within it the key to explaining the directionality of temporal processes. And so you don't need time itself to flow. Time is just like a block universe account introduced after Einstein's special theory of relativity, the Minkowski block universe. And it's the fact that the processes in time have to satisfy certain kinds of patterns or laws given by this probability distribution and the low entropy at one end of time that makes the difference between past and future. A way to put it is to say that the low entropy, which is sometimes called the past hypothesis, that deserves the name past, not because we're assuming a difference between past and future, but because it defines what the past is, because processes have to develop in a particular direction, at least probabilistically, from that point on. Now, it turns out that this probability distribution ends up assigning probabilities to every possible micro-history of the world. And this is really important to developing the physicalist program of explaining all the phenomena we see around us in terms of fundamental physics and this probability distribution. I think many physicalists have not been able to complete their project because they neglected this probability distribution. And when you add the probability distribution, you can explain things like the nature of causation, for example, which is very important to explaining all sorts of ordinary processes, from the way computers operate to the way automobiles work to volcanoes to everything. All of our ordinary macro language involves talk in some way of causation. Causation itself isn't fundamental or basic on this account, but it's itself comes into sort of emerges, but not in this strong emergent sense, but just emerges because it embodies certain patterns within this probability distribution. Does that make some sense to you, Robert?